Let's try to derive the period of a spring mass system. So in order to do that, we might need to do a little bit of recall from a few earlier videos. So the first thing that we need to recall, it's on the video where we discuss acceleration and displacement always have opposite sign. So what we do in that video is we analyze a spring mass system. So for this spring mass system here, we see that the oscillation is happening in the x dimension. Therefore, if you want to analyze the forces acting in the x dimension, we will use the Newton's second law, in which the sum of force in the x dimension equals to mass times the x component of acceleration. So we want to determine what are the forces acting in the x dimension. And to determine that, we will draw a free body diagram. And we can see that the only force acting in the x dimension is the restoring force of a spring. So we know that the magnitude of the restoring force of a spring follows Hooke's law. And we know that the x component of this restoring force of a spring is just equals to negative kx, in which the k is the force constant and x is the amount of stretch or the amount of compression that happens to the spring. So we know that this x component of the restoring force of a spring is the only force that is acting in the x dimension. Therefore, we can equate these two things together, and through this equation, we have derived the equation for acceleration. The x component of acceleration is equal to negative force constant divided by mx. Okay, so the idea is we want to determine the force that is acting in the dimension in which the object oscillates. We determine it to be the restoring force of the spring, and therefore we determine the x component of the restoring force of the spring. We determine it to be negative kx, and by equating it to mass times the x component of acceleration, we determine the equation, which is ax equals to negative k over m times the displacement x. So first thing to recall is this equation over here. The second equation that we need to recall is from our discussion of the acceleration time equation and acceleration time graph. So what we did in the section in which we relate between acceleration and time is we try to derive the equation for acceleration for two types of situation. The first situation is where the object starts from the equilibrium and moves in the positive direction, then continues to oscillate. This is the first situation in which we can describe its displacement by a sine omega t. And by doing the differentiation, we obtain the equation for x component of velocity, which is a omega cos omega t. And if we continue to differentiate this velocity equation, we obtain the x component of acceleration, which is negative a omega square sine omega t. So this is for the situation in which the object starts from the equilibrium and move in the opposite direction, move in the positive direction. So if you move on to the second situation in which the object starts from the positive maximum displacement, then we know that the displacement can be described by the equation a cos omega t. Now if we differentiate this equation here, we will get the x component of velocity equals to negative a omega sine omega t. Okay, cos differentiate, you get negative sine. Then you differentiate the omega t here, you get this omega over here. So if you continue to differentiate this x component of velocity, you get the x component of acceleration to be negative a omega square cos omega t. So why is this discussion important here is because if we rearrange these two equations, we revert the order between omega square and the amplitude, then you can see that what happens in both of these equations is at the back here we have a sine omega t, which is just the displacement equation. On the right hand side here we have a cos omega t, which is also just the displacement equation. So now we can know that for any kind of SHM, any kind of simple harmonic motion, the acceleration can be related to the displacement through this equation. Ax, the x component of acceleration, equals to negative omega square x. So we have derived an equation that relates between acceleration and displacement. And it is actually a general equation, and all simple harmonic motion must obey this equation, in which ax, the x component of acceleration, is equals to negative angular frequency squared times the frequency. And because this equation is general for all simple harmonic motion, but it's almost general, you can change it to y, you can change it to z, you can change it to theta. There are various versions, but we usually just say is x component of acceleration equals to negative omega square x. So all kind of simple harmonic motion follows this kind of equation. Okay, there might be a little bit of modification, but it always follows this kind of equation. So if call this kind of equation the hallmark of simple harmonic motion, because any kind of simple harmonic motion will have to obey this equation. So this equation sort of represents simple harmonic motion itself. Okay, so this is the second equation that you need to recall. So I've recalled two equations here, and let's try to do something with these two equations. So now we are going to actually go and derive the period for a spring mass system. We have these two equations that we recall just now, and we see that these two equations here share a similar structure. So what we do now is we compare and we obtain the fact that omega squared, the angular frequency square, is just the force constant divided by the mass of the object undergoing oscillation. So obtaining this is important because if we square it, we obtain the angular frequency to be the square root of force constant divided by the mass of the object undergoing oscillation. So you know that if we have a spring mass system, we can determine the angular frequency through this equation over here. Now this step is important here because angular frequency, once we know how to determine angular frequency, it is equivalent to saying that we know how to determine the period and the frequency already. Because angular frequency, period, and frequency are all connected together, as we discussed in one of the earlier videos where we discussed the parameters used to describe a simple harmonic motion. So now we know all three things here are related through these three equations here. We can now move on to derive the equation for period and frequency. So for period, we know that omega is equals to 2 pi divided by period. So we can substitute 2 pi divided by period over at this side over here. So we know that 2 pi divided by period will be equals to the square root of the spring constant or the force constant divided by the mass of the object undergoing oscillation. Just by rearranging the equation, we know that the period is just 2 pi times the square root of mass divided by the force constant. So this is the equation for period for a spring mass system. How about the frequency? Well, we will substitute 2 pi times frequency to replace this omega, this angular frequency over here, and we get that 2 pi frequency is equals to the square root of force constant divided by mass. So now if you again rearrange it, bring 2 pi to the other side, we know that frequency is just 1 over 2 pi times the square root of the force constant divided by the mass. So from this process over here, we have obtained the equation for period and we have obtained the equation for frequency. And well, if you notice, the equation for period and the equation for frequency are just inverse of each other. So you can actually obtain the equation for frequency or the equation for period by inversing the counterpart of it. So you can obtain this by doing this equation over here. Okay, so this is how we derive the period, the frequency of the spring mass system. It always comes from finding the equation that relates between the acceleration and the displacement for the system, compare it to the hallmark of simple harmonic motion, obtain the relationship between angular frequency and the parameters that are inside here. So once we know this equation already, it's equivalent to knowing period and frequency because we know these three parameters here are intimately related to each other. So that's how we derive these parameters for spring mass system.